Hello, everyone. Oh, this is working. You're live. My name is Amulya. I'm a principal technologist at AWS. I'm very excited to share with you Airbnb embedding platform story. So I'm going to do a pre-talk, and then I'll hand it over to the Airbnb team to talk about the embedding platform they're working on. So how many of you heard this term Gen AI or large language model? If you raise your hands. Amazing. And you also heard OpenSearch, right? And how many of you think they are better together? Thank you. You are my people. Thank you very much. So large language models are fantastic, but the challenge is they don't know your organizational data, your latest news, or the recent product you have launched. So it's like having a friend who is genius, but was living in the cave for like almost a year. It's not very helpful. Or it is like a printout of Wikipedia, which is 1 year old. It's not very helpful again. So how can you augment your organizational data and get the best out of your Gen AI or LLMs? There's a simple recipe for that. So you gather all your data, you pick an embedding model, which can be any embedding model, and you create vector embeddings. Now, vector embeddings are just series of numbers, and the reason why they're just numbers because large language model or AI better understand number than text. And you can create embeddings out of images and audio as well. Now, you need a place to store all of this, and that is OpenSearch as a vector store. Once you have all of this data in vector space, it will enable you to create multiple use cases. For example, you can create similarity search by looking at how the proximity of two objects in the vector space within OpenSearch. And it can also enable you to get best out of your LLM, large language model, or your Gen AI investments. Let's look at one use case that is basically augmenting your large language model with your organization data with something is called as retrieval augmented generation. So you start with the user input, which is basically a prompt in its first form, and then you couple it with the situational context you have, the conversation history the user is having with the large language model. But that's not enough. You need to give the large language model the information about your organizational data. And that's the semantic context with OpenSearch vector space, because all of your data is already available in the vector space as embedding. And OpenSearch vector space can add that semantic context. At the end of it, you get an engineered prompt, which is a lot better, has the latest data about your organization or the latest products you have, and you get a better results and better use from your large language model or Gen AI investment. So with that, and to dive this further, I would like to call upon Moutupsi Paul and Xiaotang on stage to talk about how they have done something like this at Airbnb. Thank you.
Thank you, Amulya. Hello, everybody. Welcome to our talk. And today, we are going to talk about Airbnb embedding platform and how we use OpenSearch as a vector store to power it. Again, I am Moutupsi Paul. I am a software engineer at Airbnb, and later you are going to hear from Xiaotang, who's also an engineer at Airbnb, and we both work at Search and Knowledge Infrastructure team. This presentation is arranged into 4 sections. We are going to talk about how we use embeddings at Airbnb, followed by a brief overview of our embedding platform. Next, we are going to discuss how we use OpenSearch to power this platform. We are also going to deep dive with an image search use case. And finally, we are going to share our learnings and optimization strategies that work pretty well for us. Before this, let's do a quick primer on what embeddings are. As Amulya mentioned, computers understand numbers better, so embeddings are a way to represent data like words, images, videos into a list of numbers called vectors. This vector represents the original data by encoding its essential features. And in simplest terms, embeddings translate things and concepts into numbers. And since vectors are a list of numbers, we can also visualize them as points in an n-dimensional space. In this quintessential example, we use embedding models like word2vect to convert English words into points in a space such that similar words like man, woman, or woman, queen appear closer to each other. To find similar words, we convert the query word into a vector and then compare against all the data points in the vector space to find nearest neighbors. This concept is at the essence of how vector similarity search works. This information-rich way of representing data using numbers allows computers to find similarities and patterns within the data. For example, in a video search system, we can search for how to fix bike chain, and the video system uses embeddings to compare this incoming text query to find the relevant tutorial, even if the video tutorial does not have these words per se. In an online shopping, if a user frequently visits or views sporting shoes, we can recommend similar products by using product embeddings. Let's look at a few ways in which we use embeddings at Airbnb. Similar listings. Similar listings is a recommendation system that suggests alternate Airbnb options for the current dates. This, under the hood, uses embeddings, encoding features like listing location, type, architecture, style, etc., to measure similarities between listings. We also have an internal product stack that allows you to search across millions of Airbnb listing pictures. They can be searched either using pictures or text. A search for a treehouse adventure should return treehouse listing images. A search with a dream ski vacation picture should also return ski listing pictures. Further, these searches can be constrained using listing location, number of reviews, ratings, and so on. This search system also uses embeddings to return relevant results. Later in this presentation, Xiaotang is going to deep dive on how we do this efficiently. Location reconciliation. As a travel company, our knowledge graph is rich with location information. We consolidate data from different sources and match them against the entities in our knowledge graph before enriching with new attributes. And as you noticed, it's not necessarily a trivial problem. Not all Mount Shasta locations mean the same thing. To solve this, we use location embeddings with geofilter to generate candidates before reconciliation. Now that we get an idea of how we use embeddings at Airbnb, let's take a look at our Airbnb embedding platform. We also call it AEP. In single sentence, it's a platform solution to generate and search for vector embeddings. With the popularity of large language models in late 2022, early 2023, we saw a significant increase in ideas using embeddings. So instead of each team investing in a solution, we invest in an unified infrastructure with the goal of powering all embedding use cases at Airbnb. We designed this platform to be declarative. Tenants define what they want, and we execute based on that contract. Given large language models and vector search is an active field of research, we also want the system to be extensible. A unified API must hide all this internal detail and variation behind a simple interface. And since we support multiple use cases, they must be isolated from each other. Disruptions caused by use case 1 should not affect use case 2. With this design principles in mind, this is what we have built so far. We are still building. This platform is still new, so this is what we have so far. Our system, AP, knows how to generate embeddings from raw features and build indices out of it to support semantic search. We also support vector search with filters. We have an orchestration layer to periodically update or rebuild indices and deploy them with zero downtime. Besides this, we also maintain compute resources needed by a high-performance, resilient search system. This is a bird's-eye view of all the components and services that interplay with each other to achieve an end-to-end solution. The user plane here builds different tools, allowing users to interact seamlessly with AEP. Our API server is the gateway to the system. It routes incoming queries to one or more components of the system. The embedding generation components is responsible for transforming raw features into embeddings. It is also responsible for generating well-defined entities with vectors and metadata and materializing to our data store. Once the entity documents are built, we trigger the vector similarity search components. The vector search components, which is this guy over here, takes the materialized entities and executes and triggers ingestion workflow to build search indices. It is also responsible for interacting with vector DBs like OpenSearch, transforming requests and responses as needed. Besides OpenSearch, we also have ANN in a box kind of setup that runs raw search libraries like Lucene or HNSW-lib directly on a Kubernetes pod. For this Kubernetes setup, when an index build workflow gets triggered, we use data processing platforms like Spark to build indices offline and save them to an index store. This indices later gets pushed into serving nodes for executing searches. Isolating index builds and searches this way allows us to achieve high indexing throughput without affecting or interfering with search latency. The OpenSearch setup is slightly different. For OpenSearch, we use build APIs on the serving cluster and create new indices and then back them up in the index store. This sometimes causes CPU contention between the indexing and the serving workflow. We are still on OpenSearch 2.13, but later in the slide, we are going to talk about how we get around this contention. So now that we get an idea of different components of AP, let's take a look at a typical onboarding workflow. Onboarding to AP is a three-step process. First, we author schema to define the data models, the index configurations. This basically tells our system what and how we want to process the data. Once the schema is defined, AP triggers the data processing pipelines to generate embeddings and build search indices. Once an index is built, we push the indices to the query nodes, and we are ready to execute vector searches. I mentioned 3 steps, but there is always this hidden 4th step iteration. Large language models or indices often need to be parameterized or tuned, so we have to iterate through these configurations to find the right setting that works for this particular use case. Let's take let's look a little bit more into what each of this onboarding step may look like. So the first step is defining schemas and configs. Our schemas are broadly grouped into 3 categories. The entity collection schema defines the input and the models. For example, if you want to use word2vec, BERT, OpenAI, ChatGPT model, and so on. The index schema defines how the data needs to be indexed, what kind of index you want to use, HNSW, IVF, or brute force, what kind of HNSW parameters you want to use, what kind of search filters you want to use, geo filters, categorical filters, range filters, and so on. There's also a third configuration, which allows users to tell us about the schedule of how frequently or when the data should be pre-processed, regenerate the index. This is basically a way to refresh the system. Once all of these configurations are defined, it's time for us to crunch the data. This is a typical data processing workflow. It's an offline data processing workflow that generates the embeddings and also builds a search index. An incoming build request starts with generate batch embeddings request, which then internally triggers the offline inference and the offline, wait, my pointer is not working, but anyway. So I was saying that the generate embedding batch request internally triggers this offline inference and data management workflow. The inference step uses the models configured in the entity collection schema to build embeddings from the raw features. Once embeddings are generated, we package them along with other metadata that may be needed for filtering into a well-defined entity document and save them to the data store. Once these entities are generated, we start building the search index. An index build request to the vector similarity component triggers the index build workflow. And this workflow looks at the index schema to build all the necessary indices. Finally, once the indices are built, we save them to the index store to be pushed later for searching queries. This is how a search query flow may look like. An incoming search request also triggers the online inferencing to convert raw query features into an embedding. This query vector, along with other search filters, are forwarded to the vector similarity engine. The vector similarity engine runs transformations as needed and finally forwards them to the OpenSearch, which returns results. Once we have these raw results back, we transform, or rather convert these raw responses into a well-defined search response and return them to the users. Let's talk a little bit more about the fourth hidden step, which is iteration. As mentioned earlier, iteration is a necessary step in the development workflow. A user edits the schema to maybe update the model config or the index parameters, and then triggers the data processing pipelines to rebuild the indices with this new configuration. This new index is then evaluated with metrics like recall, NDCG, or hit rate until the evaluation results meet the exit criteria. The cycle keeps repeating itself. AEP's declarative nature simplifies this process of iteration, but it may still take a while for this whole cycle to converge. To reduce this overhead, we are currently working on building this evaluation framework that allows user to systematically find the right set of schemas, the right set of configurations that works well for them. With this, I come to the end of our brief overview to our Airbnb embedding platform, and I'm going to hand it over to Xiaotang, who's going to talk more about how we use OpenSearch as a vector DB to power our embedding platform.
Yeah, thanks, Moutupsi. So hello, everyone. My name is Xiaotang, and I will be talking about how we use OpenSearch as a vector DB and how it is integrated into our embedding search platform. So first, why did we choose OpenSearch as one of our vector DBs? For AEP, OpenSearch stands out as a great choice due to its scalable and distributed architecture. It is designed to efficiently handle large-scale, high-dimensional vector data, making it ideal for applications with large datasets and complex search queries. It offers native support for k-nearest neighbor search and approximate nearest neighbor search, enabling fast and precise vector similarity queries. A key feature is that it supports multiple embedding search engines, namely FICE, NMSLib, Lucene, giving us the flexibility in how we process and retrieve vectors, allowing us to choose the best option for each specific use cases. Another strength of OpenSearch is its seamless integration of traditional keyword search with vector search, enabling hybrid searches that combine text-based relevance with vector-based similarity. It also supports embedding search with filters across multiple engines, which is an essential functionality that is needed by many of our use cases. Finally, being open source, OpenSearch is actively developed by a community. which ensures continuous improvements in performance and feature support, making it a strong contender for VectorDB use cases. So how do we integrate it into our Airbnb embedding platform? As Moutupsi has mentioned, as a platform serving from multiple query engines underneath, we define both index schema and document structure in a unified format, ensuring that we can generate consistent and extendable configurations to streamline the integration with OpenSearch during the index generation and the data ingestion. Our index builder transforms the structured data into the OpenSearch compatible index mappings and JSON format documents automatically. We handle the setup of embedding by defining key parameters such as the embedding engine, space type, and the vector dimensions, etc. We also configure index settings such as number of replicas and shards, and then transform all this information into the OpenSearch index configurations during the generation process. In our platform, the index management strategy, one of the key aspects is that we support both bulk rebuilds and incremental data updates. It allows us to refresh our entire index when needed, ensuring the data accuracy and completeness, while also enabling us to make quick, targeted updates as new data comes in. This dual approach ensures that our indexes are always current without unnecessary overhead or downtime. When it comes to index management in OpenSearch, we rely on index aliases, and when these aliases act as pointers to our indexes, allowing us to switch from old to new indexes, and this also means that we can update our serving data behind the scenes without any disruption to user experiences. Furthermore, we employ snapshots for index builders, index rebuilds, and disaster management. Snapshots provide us with a reliable way to restore our indexes and to previous state if needed, adding an extra layer of security and stability to our platform. Next, let's take the image search as an example use case and take a look at how OpenSearch works in action as our VectorDB. So in this slide, we are looking at a part of a real schema for the image search use case. This schema demonstrates how we structure the OpenSearch index with KM vectors. And first, we can see that this country code field is an example of traditional keyword search fields. It is a type of keyword. It is stored in the index and allows us to apply filters during the KM search, narrowing down the results by listing countries. And of the core of this index is the embedding field, which is defined as a KM vector with a dimension of 1024. This vector represents the image embeddings that we generate from our models, allowing us to search for similar images based on their vector representations. And we're using the Lucene engine with the HNSW algorithm for building this index. This setup is tuned with specific parameters like EF construction and M to optimize the performance of the vector search. Next, talking about some numbers. In this image search use case, we are working with a large-scale data set, over 200 million documents, which result in an index size of around 6 terabytes without extra replicas. And this index size includes embeddings and a metadata field. And to manage this efficiently, we configured the index into 80 shards, and this configuration helps optimize both write and read performance by distributing the workloads across multiple shards. However, due to the sheer size of the data, each bulk ingestion process takes several hours to complete. One of the key challenges that we've faced during these injections is the high CPU usage during write, which has become a concern for us as it impacts the performance of other operations running in parallel. As for the performance and optimization strategies, we will cover them in a later section. Next, I'll talk about the searching part and how we use OpenSearch to perform vector similarity searches. So when a query is initiated, we first transform it from the defined query schema from our platform into the specific query language used by OpenSearch. And this enables us to execute KNN vector search with filters, allowing us to combine this vector similarity with traditional filtering for more precise results. After OpenSearch processes the query and returns the result in its JSON format, we transform those responses back into the format that our platform understands. And this transformation on both the input and output side ensures that OpenSearch fits naturally into our overall embedding search framework. So going back to our example of the image search use case, this slide illustrates how we perform vector similarity search in OpenSearch with the addition of a filter. So we are searching for the top 10 closest embeddings, applying a term filter with only results of country, United States of America. So what is notable here is that the filter here is put inside of the KNN query clause, which triggers the so-called efficient KNN filtering that OpenSearch supports. And this is a hybrid filtering approach that applies filtering during search rather than just before or after the KNN search. So this guarantees that if there are enough matches, we will always get exactly K results. So this efficient KNN filtering is supported in OpenSearch by multiple engines, including Lucene engine with HNSW algorithm, and the FICE engine, which offers both HNSW and IBF algorithms. This flexibility allows us to choose the best algorithm for our various use cases. Some more on the numbers. In this image use case, we actually managed to achieve a 92 recall rate with k equals to n. And also for this use case, we managed to have a P95 latency of 280 milliseconds, which is good enough for this internal use case. OK, there is the 92%. OK, so yeah, going to the next slide. In our embedding search platform, we used the managed service solution when using OpenSearch, and I will go ahead and share our experiences on the pros and cons of this approach. Starting with advantages, so simplified operations are a key benefit because we don't need to manage the infrastructure or maintenance tasks manually, and this lets us concentrate our core work without worrying about the underlying system management. Another major advantage is its scalability. There are flexible scaling options that can adapt to different use cases, allowing us to balance performance and cost efficiently. And this dynamic scaling ensures that we can handle varying data volumes and query traffic efficiently during the different configurations. So with built-in monitoring, we benefit from the integrated tools that help us monitor the performance without also additional configurations. Finally, snapshot and backup support is provided through the automated snapshots, which are crucial to disaster recovery and index rebuilds, ensuring our data integrity and resilience. So these features collectively enhance our operational efficiency using OpenSearch and its reliability as well, and allows us to focus on leveraging OpenSearch to meet our specific needs. Next, I'll discuss some of the challenges associated with using the provisioned OpenSearch cluster. So first is the cost consideration falls on the users, so it requires some careful attention. We also need to strike a balance between selecting appropriate machine types that meet our scalability needs, and this to ensure that we can optimize both our cost and performance without overcommitting on resources. So performance tuning is another area of focus, particularly with the high CPU usage. During bulk writes, it is crucial to balance read and write operations to manage performance effectively while controlling cost. Finally, the learning curve itself is a set of difficulties for ourselves. It is challenging to navigate scaling cost and making cost-effective machine choices and utilize the right tools to do the debugging and optimization. Mastering these aspects required time and careful management to leverage the full potential of the cluster. Next, I'll share the lessons that we have learned and some of the things that we have done so far to maximize the efficiency of our OpenSearch Vector DB. And most of the work I'm going to mention here are done here attributes to my incredible coworker, Tomas Fernandez-Lobe, who is also an active contributor to Lucene and has extensive experiences with OpenSearch. So before entering the realm of OpenSearch, of vector search, our team members have some experiences previously using OpenSearch and other Lucene-based search engines for a while. However, it quickly became clear to us that with vector search, there is a fresh set of challenges. And in this next few slides, we will show some of the learnings that we have while building the platform and onboarding our clients. So starting from the right side of the story, we're going to show some numbers, and most of the numbers here are specific to the image search use case that we have been mentioning. Compared to the traditional indexes, the first thing that we noticed with the KNN indexes was that building the index has become more expensive. So writes has always been relatively more expensive operations in Lucene, but with HNSW graph, this is more so than before. Here are some of the numbers regarding the index ingestion time. So everything being equal, in our experiments building the same index of over 200 million documents with 80 shards, vector dimension of 1024, it took us twice about the time to write with than without KNN. And these numbers are based on this Lucene index. However, we also got similar numbers with the other engines as well. And in our effort to improve the write performances, the first step was to look at the metrics to understand what the bottleneck was. And looking at this graph, there was no doubt that we were CPU bounded. The CPU usage would stay at 100% almost all the time during our write jobs. And by the way, these jobs are triggered by our Spark jobs. So the good thing is that OpenSearch has these nice hot threads APIs that give us information about which threads are hot and what they're doing. And by checking through this API during writes, every time we saw some similar patterns. We saw that merges were taking about 90% of the CPU time. And particularly this class, incremental HNSW graph merger. So it was not necessarily the write itself that was taking the most time, but the merges of the segments that were created during the writes. To tackle this, we completely disabled autofresh and also increased the number of maximum transaction log size. With those changes, we saw less merges happening. And although after this, the CPU usage still remained at about 100%, the delta write time in our image use case went from 1 to 2 hours down to 15 minutes. Now we know that writes are more expensive and bring unexpected extra workloads for the nodes. Here are some of the actions we already took and want to take for the future and to be able to handle the writes better. So first thing was straightforward. We added a throttle on the write KPS, which controlled the writes at a steady rate and while it's still acceptable and fast enough. Second, we removed the replicas while building. And this is because we know the nodes performing writes were very busy. We try to reduce the number of those that have to do the task. Maybe this is not something that everybody can do, but for an application that needs to serve traffic while write, for example, probably you cannot do this. However, in our current architecture, we only serve after the index is fully built. So this is something that we did, and it really helped. Third, we reduced the number of segments that were flushed to disk to reduce the amount of merging. And this isn't new to Lucene, of course, but this is even more important now than it was before. For us, we removed the auto refresh completely, but if you cannot do this because we need fast access to the writes, at least reduce the frequency as much as possible, because the default of 1 second is not ideal now. And we need to make sure that the maximum transaction log and the buffer size are big enough. Lastly, if possible, use dedicated nodes for writes. This is not something we're doing yet, but we're looking to see if we can have this in the future. So after implementing all that mentioned above, now with our bulk ingestion, the graph looks much better. Write time stays roughly at the same, a few hours. However, the CPU usage stays on average under 70%, which makes the reads and other operations that run on the cluster during this time less of a worry. And next, I'll hand over back to Moutupsi, who will talk more about how we optimize on the reads.
Thank you, Xiaotang. Hello, everybody. I'm back. So let's look at a few strategies that worked for us to improve our read latency. Different use cases behave differently, so trying out different combinations of engines, distance metric, and parameters of the HNSW index itself worked better for us because it helped us figure out the best setting. For our image search use case, we saw Lucene perform better than other engines, though others have reported FICE working better than Lucene. We didn't yet test with the NMS lib engine support since our platform needs filtering, and that option does not support filters. Also, in our case, we didn't see much difference in latency while testing with different MEF construction parameters for the HNSW index, though we know of other use cases that saw a big jump or a big difference when tuning them. What worked very well for us, however, is reducing the number of index segments. This is something that typically does not have that much of an impact with regular lexical text-based searches in Lucene, but we did see a big improvement when we tuned them. Our image search use case does not need constant real-time updates, so we can afford to batch update the index once every day and keep the number of segments somewhat static. But since force merging segments take a while, reducing into a one big segment also doesn't work well. 10 is a sweet spot that worked well for us. There is currently some work on parallelizing search within segments or the index reader-writer separation that may also help, but this is something that works well for us now. Another big learning is staying up to date with OpenSearch, especially if you are using the Lucene engine. This area gets a lot of improvements very rapidly. So we upgraded from OpenSearch 2.9 to 2.13, and everything else being equal, except the distance metric, gave us a big improvement at both read and write. We are hoping to upgrade to newer versions of OpenSearch to take advantage of SIMD or index reader-writer separation. So this is at the end of what we have so far. Let's look at what we are working towards. This Airbnb embedding platform is fairly new. We mostly only have bulk index updates or delta index updates to refresh the index. But currently, we are also working towards near real-time updates. We want to reduce our time to search. Though it's OK with our current use cases, in the future, this is not going to work. The other thing that we are looking at is OpenSearch serverless. As we talked about in the previous sections, there is a lot of resource interference between the reader and the writer. And OpenSearch serverless can work pretty well here since they separate these aspects completely. So we are also looking towards integrating OpenSearch serverless into our platform. The other thing that we are working towards is building this evaluation framework. We have mentioned earlier how there is this fourth iteration step for almost every embedding workflow that needs one to find that right settings around large language models or index that works. We are trying to build this framework to allow our users to systematically find that setting and optimize for both latency, cost, and quality of search results. And finally, we have a handful of use cases already into our platform. We are working towards onboarding more and more. And as we do that, we are smoothing our rough edges, improving our onboarding experiences, adding more and more features iteratively, and also improving our resiliency as we go. And this brings to the end of our presentation. Hope you had a good time. We can open the floor for questions.